All right, in this video, I'm going to be doing some more double integral examples. I'm going to be working through the practice test for multivariable calculus for 3-1, at least this year. Okay, we're going to write but not evaluate a double integral that represents the volume of the solid. Okay, so I'm going to start by drawing you the solid, and then I'll write a double integral that represents it. Okay, so 1a is, all right. Okay, so x, y, and z, this is 2 and 2 and 3. We're talking about, okay, that thing that I just shaded, that's the graph of f, which is f of x and y equals 2 minus x minus 2/3 y. So I'm going to say, okay, it's going to be a double integral of f, because it's a volume. So 2 minus x minus 2/3 y. Okay, but then it's dA, and it's like, is it going to be dx dy or dy dx? And so what we need to do is we need to get ourselves the region that we're integrating over, and it's going to be that little kind of triangular region in here. But maybe we just go ahead and draw ourselves a little xy plane. And, okay, where y equals 3, there's an intercept, and where x equals 2, there's an intercept. So we go ahead and draw that line. And this is the graph of y equals 3 minus 1.5x. Okay, and it looks like that's the upper bound of the region, right? Because it goes back to the origin, okay, from there. So just need to say, all right, y is running from the x-axis up to that diagonal line, so that's y equals 0 up to y equals 3 minus 1.5x. So I need to integrate with respect to y first, right? Because it's y equals 0 and y equals 3 minus 1.5x. Okay, and then x needs to go from 0 to 2. Okay, and that's us writing an integral that represents the volume of that solid. Okay, 1b is going to be, it's a half sphere, and I know better than to try to draw this myself. It's pretty much the half sphere, or no, it's a quarter of a sphere. Where z is positive and y is positive, but x is running from basically negative a to a. Okay, so I'm going to just draw you the region that we're integrating over, and that's in the xy axis, or in the xy plane. It looks like that. Okay, where it goes from negative a to a. Okay, and then maybe I'll do this both ways, in rectangular and polar. But you know, on the test, this question, or the related question to this, it directs you to use polar coordinates. So this is g of x and y equals the square root of a squared minus x squared minus y squared. Yeah, that's, I think I mistyped it. Yeah, that's going to be x squared plus y squared plus z squared equals a squared. Yeah, that's what it's supposed to be. And maybe I fixed it by the time you're looking at this. Okay. And so now I know it's going to need to be a double integral. Okay. I'm going to say y is going to run from 0, from the x-axis, all the way up to the graph of that. And I know that's the positive, y equals the positive square root of a squared minus x squared. So, all right. Double integral using dy and then dx. Okay, well, it's going to be g that I'm integrating, and I just as soon not write that again. And y is running from y equals 0, that's the x-axis, up to that circle, so that's the square root of a squared minus x squared. And then x is running from negative a to a. Well, that's doable. Okay, but if we needed to write this in polar coordinates, I would say, all right, I'll just redraw the region of integration. Okay, to me, that looks like r is running from 0 out to a, and theta is going from 0 to pi. Okay, now I'm going to say, all right, this is the double integral. Okay, g, to change g into something with polar coordinates, that x squared and y squared, that makes an r squared. So x squared plus y squared is r squared, so I've got a squared minus r squared. And then remember that dA is r dr d theta. Okay, r runs from 0 to a, and theta runs from 0 to pi. Okay, and that's going to be the polar setup on that exact same situation. All right, number 2. Okay, find the amount of volume above the paraboloid and below the half sphere. All right, this one, I'll tell you the version of this question that's on the test is, it also comes with a little more information about the intersection of those two surfaces. I think you can see based on the kind of the roundness of both of these things that the intersection is going to be a circle. And I'm going to just show you how you would get that. So first we're going to need to, okay, so it pretty much looks like, maybe I can try to draw you that. Okay, that's the sphere. This is the paraboloid. The intersection that I'm interested in is going to be a circle. I'm going to kind of just cut it in. I don't really think I can draw this very accurately, but it's going to be like along there and around the back. Okay, and that's the thing that I'm interested in finding. If I'm interested in finding those things, I need to set the two equations equal to each other, right? So I'm going to say x squared plus y squared equals the square root of 25 minus x squared minus y squared. Okay. I'm going to square both sides. So x squared plus y squared squared is going to be x to the 4th plus y to the 4th plus 2 times x to the 2 times y to the 2. And that's going to be equal to 25 minus x squared minus y squared. So the set of all points on the intersection is x to the 4 plus y to the 4, okay, plus x to the 2 plus y to the 2 plus 2 times x to the 2 times y to the 2 minus 25 is equal to 0. Now you can go and you can graph that, but it's circular. Okay, and it's like that's not really helping at all. So, and you know, on Wolfram alpha or whatever, it's not really going to give you anything. But if I know that that intersection is a circle, and I also know that this is the equation or an equation that represents it, I'm going to go in and I'm just going to find the radius of the circle because I know it's centered at the origin. I can find the radius because I'm going to switch this to polar. These things are very round. You know, look at all these x squareds and y squareds. Okay, I'm going to find the radius of that circle by solving that equation where y is equal to 0. I'm going to maybe give you a sketch here in a second. And then I'll have balanced integration for when I switch to polar. So, okay, to give you the image of this onto the xy plane, okay, the intersection is a circle, right? And we just need to figure out what the x coordinate is right here, because that will give me the radius. Okay, the y coordinate right here is 0, so I'm going to let y equal 0. So I'm trying to solve the equation x to the 4 plus x to the 2. Okay, anything with a y in it is going to 0, so minus 25 is equal to 0. We can do that. Okay, so I'm going to go over here to my calculator. Make sure I'm in function mode. I've been doing some polar stuff in my AP calculus class lately. So I'm going to go over here to y equals, and I'm going to say y equals x to the 4 plus x to the 2 is 25. And I'm just going to be interested in where that equals 0. And maybe I'll just assume standard. Okay, look, that's a good sign. I'm seeing it happening at two different places. They are evenly spaced around the origin, or at least it looks like. I don't know, 0 to 3. I get 2.127. I'm just out of curiosity. I'll look at the other one. Maybe we don't need to say that. -3. Okay, yeah, no, it is the same. Okay, it's just like the way it's sketched on the calculator was not entirely accurate. So I know that my region that I'm going to be integrating over, right, the stuff that's underneath the sphere and above the paraboloid, is just going to be sphere minus paraboloid, and I'm going to add it up over that whole region. Okay, so I know that that is 2.1271901. Okay, so that's going to be r. R is going to run from 0 to that number. Theta is going to go from 0 to 2 pi. So now I was interested in doing the double integral of, okay, sphere minus paraboloid. What is that? Z equals x squared plus y squared. Okay, dA over the region R. But I'm going to do this by switching to polar, right? And so this is going to be the square root of 25 minus r squared multiplied by, or minus r, multiplied by r dr d theta. Okay, we're going to let r run from 0 to 2.127, the rest of the number. And then theta going from 0 to 2 pi. This is going to require more. Okay. So what I'm going to want to do here, I'm going to be interested in, make sure my paper's lined up, and then I'm going to kind of distribute it in here. Okay, so this is the integral from 0 to 2 pi of the integral from 0 to 2.1271901 of r times 25 minus r squared square rooted. Now, if you were desperate and you're like, I don't want to anti-differentiate that, or I don't know how to anti-differentiate that, you could reverse. Actually, I think I might do that, because then it'll just be taking the antiderivative of this with respect to theta, making that happen, and then I could run the outside integral using a calculator. So I think I'm going to do that. I think that's going to be the way to proceed. So this is not, I mean, like, I could use a U substitution there, right? You've probably already done it at least once in this class, using a U substitution on this type of polar object. But I just don't exactly feel like it. So 0 to 2.1271901. And then I can just use a calculator for that computation of the integral from 0 to 2 pi of this thing, r square root of 25 minus r squared minus an r squared d theta dr. I distributed in that r. Okay, and well, I know how to do this with respect to theta. It's just going to be this thing times theta, as theta runs from 0 to 2 pi, so it'll just be 2 pi times that. So I know that this is 2 pi times the integral from 0 to 2.1271901 of r square root of 25 minus r squared, subtract r squared dr. That's a job for the calculator. Okay, so I'm going to bring that in. Maybe I'll do that a little bit. That'll help. Okay, so 2 pi times the integral from 0 to 2.17271901 of r times the square root of 25 minus r squared minus an r squared dr. We get 47.598. That was kind of a lot, but if, like I said before on the test, they give you information about the intersection, so all the stuff in red is not necessary, and so it's, it's not bad if you're given the intersection. And the intersection works out nicely. That's the other thing, this intersection. I tried to mess with it and try to get it so that it intersected, trying to leverage the 3, 4, 5 triangle relationship. I just couldn't figure it out, but I was also in a hurry, so I didn't give it that much time. Okay, r is bounded by x equals 0, y equals 4, and y equals 2 to the x. Compute the double integral. Okay, that's going to be right up our alley. Okay, so there's number 3. I'm going to draw a picture of r right down here. Okay, 2 to the x is there. Y equals 4. that's x equals 0, and over here would be x equals 2. And we'll need that eventually, I guess. All right, for a, I'm interested in integrating x cosine y dy and then dx. Okay, so y in this thing is running from 2 to the x up to 4. Y equals 2 to the x is on bottom, y equals 4 is on top. So I'm going to put that. X running from 0 to 2. Okay, I can do this. I can anti-differentiate this with respect to y, and I'll have x times sine y. As y runs from 2 to the x up to 4. Okay, then I'm going to, what am I going to do? Oh yeah, actually plug in 4 and 2 to the x, and I'm going to be taking the integral from 0 to 2 of x times sine of 4 minus x times the sine of 2 to the x dx. This must be done with a calculator. There's not going to be an antiderivative for that. It's not going to happen. So maybe I'll bring that in here. You don't need to see that anymore. Okay, and this is the reason I'm allowing you to use calculators, so I can give you interesting integrals like this. X times the sine of 4, I'm in radian mode, minus x times the sine of 2 to the x, okay, dx, not plus, that's it. Okay, and I get negative 2.182. And I feel like that's actually pretty believable because cosine y does eventually go negative after y equals pi. And yeah, so, you know, there's going to be some negative area. And yeah, I can see how that would happen. Okay. So negative 2.182. And then for 3b, let me just cover them. For 3b, same region, we're interested in computing the double integral over r of x minus y dx and then dy. Okay, so I'm going to say, all right, first is x, and so x is running from x equals 0 and equals, who knows, on the right. So I need to solve for x in this equation. So if y is equal to 2 to the x, I'm going to take the log with base 2 of both sides. So log with base 2 of y equals x. Okay, so now I'm going to be integrating x minus y, but as x runs from x equals 0 to log base 2 of y. Of x minus y dx and then dy. And what is y running from? Y is running from 1 up to 4. Okay, so I'm going to anti-differentiate with respect to x, so I'd have 1/2 x squared minus xy, or yx, however you want to call it, as x runs from 0 to x equals log base 2 of y. And integrating that with respect to y as y runs from 1 to 4. Okay. Now, if you don't have the button with the log base on your calculator, you can say that log base 2 of y is natural log of y divided by natural log of 2, and that's going to be the way to attack that. That's how you type in a log with a different base in an old calculator. But I need to actually do this, so okay, when x equals log base 2 of y, I'd have 1/2 minus x equals, so y log with base 2 and argument y, and when x is 0, it'll all go away. So that'll be just that. Okay. Now this is, again, a job for the calculator. That's why I put that 2 to the x one on there, right, for the calculator. So integral from 1 to 4 of 1/2 of, I don't even remember where it is. Yeah, here it is. Base 2 and argument y, close that off and square it, minus y times log with base 2 and argument y. Okay. that parenthesis for? Okay, I think those parentheses are matched up. And I get negative 7.887. Okay, that also seems believable because over here, x minus y, for the most part, y is bigger than x in this region. Okay, so 7.887. Okay, that's all I got. I'll tell you, these are not the only problems on the test, right? There's a bunch of other regular old-fashioned integrals that we've practiced a lot. There's one where you have to reverse the order of integration because it's not anti-differentiable if you don't. But these are the ones that looked a little different from the things that you'd seen on the homework. Okay? So thanks for watching.